Okay, it's time for us to do some practice with problems which involve continuity and the intermediate value theorem. As always, you should make sure to do as much as you can on your own before watching this, and in particular, as you're watching, make frequent use of that pause button. Only try to unpause when you're either already figured it out or you're completely stumped and you need a little clue about how to keep moving forward. The more you can do on your own, the better that you're going to be, and we want you to be great. All right. Well, let's begin. Find a and b so that f of x is a continuous function. So f of x is a piecewise function. It's built up of three little pieces. 3x squared if we're below -1, ax plus b if we're between -1 and +1, and 4x squared plus 1 if we're above 1. Now, if we think about these individual functions, we see a polynomial, which is a quadratic, then a line, which is a polynomial, and then another quadratic. All of these are nice functions. And so we say to ourselves, is there any problem? Well, not within the functions, so the only potential problems are where we glue things together. So in other words, when we put them, we don't want to have them where they line up in a bad way. We want to make sure that when they come together, they match up. So that's our goal, is how do you figure out how to set it up so that when things come together, they all match up. So here we go. We know we have potential problems at both -1 and +1. So how do we solve our potential problems? Well, let's actually see what we need to do to make sure it's not a problem. So we want to make sure that the limit exists. And since they're piecewise, we're going to take a limit from both the left hand and the right hand side. And so from the left and the right, we get the same value, then we're good to go. So let's think about what we do. We're going to say, take a look at the limit. So let's suppose we start with -1. As x approaches -1 from below of f of x has to equal the limit as x approaches -1 from above of f of x. Okay, let's explore this completely. Then we're going to repeat the process at 1. So let's think about what it is. Because we're coming from below, which one of our three pieces do we need to consider? Well, there's only one piece which is defined below -1. It's the 3x squared. So this becomes the limit as x approaches -1 from below of 3x squared. How about from -1 from above? Now notice we have two candidates because this part, -1 to 1, is definitely above -1, but this part above 1 is definitely above -1. Which one is the important one? Well, the answer is we always are asking what's happening right near, because that's what limits do. What's happening nearby? So we want to know what's happening near to -1. So we're going to take the one that borders. So we want the part which is right bordering -1. So that becomes the limit as x approaches -1 from above of ax plus b. So now we have polynomials. Can we do these? Well, yeah, because now that they're polynomials, we know how to do the limits. We just plug in. So we plug in -1. We have 3 times -1 squared is 3. Here, we'll get -1 times a plus b. So that's minus a plus b. All right, good. Now, that tells us that whatever the right choice for a and b are, it has to satisfy that minus a plus b is equal to 3. Okay, we're not there yet because that's not enough information by itself to tell us what a and b should be. But it's telling us sort of we're on the right track because now we have a constraint on a and b. And we're like, well, when we did it at -1, we got a constraint. Let's go for a second constraint and let's repeat the process. But the difference will be we're going to go, instead of -1, we're going to go to +1. So limit as x goes to positive 1 from below of f of x needs to be equal to, if it's going to be continuous, the limit as x goes to positive 1 from above of f of x. Now, similar idea. Which part do we grab? Because there's three candidates, because there's three pieces. We want to be below 1, but really we want to be just below 1. And the part that's just below 1 is the line, ax plus b. So this will be the limit as x approaches 1 from below of ax plus b. That's got to be equal to, now if I'm just above 1, then I'm the 4x squared plus 1. So limit as x approaches 1 from above of 4x squared plus 1. So what do we get? Well, plug in 1, we're going to get a times 1 plus b, a plus b. Plug in 1, we get 4 plus 1. So we're going to get 5. All right, now that tells us that a plus b has to equal 5. So, good. Now, that's a second constraint. So let's write them down right next to each other. We have minus a plus b needs to equal 3, and a plus b needs to equal 5. Now, two equations, two unknowns, the bread and butter of calculus. We do this all the time. In fact, here, we can see if we just add the equations together, we can get the a's to cancel. So if we add, we'll get the a's gone, a b and a b makes 2b. Or is it not 2b? No, it's 2b. 3 plus 5 is 8. Okay, so that tells us that twice times b equals 8, so b equals 4. Now that you know what b is, just plug it in. If b equals 4, 4 plus something gave us 5. Well, that tells us that a has to be 1. And there's our answer. So we need to choose b equals 4 and a equals 1. All right, now that's the way to do the problem algebra-wise. Here's a way to think about the problem more geometrical. So what do we have here? Well, what we have is the piecewise function, and they're not so hard to figure out. So I look like 3x squared if I'm below negative 1. Now, if you plug in negative 1, you see that you get positive 3. So I'm just going to sort of mark off a point here. So here's negative 1. Here's positive 3. And now what's happening is I have this parabola. And so I'm taking the parabola that's part of it below negative 1. So it's going up. All right. Now, what if I'm after 1? Well, if I'm after 1, let's see, 4 plus 1 would be here at 5. Again, you can see it's a parabola that goes up, and so it's again another parabola, maybe going up a little bit steeper. Now, what are we doing? The thing is that what happens on the far left and what happens on the far right are predetermined. We have no flexibility. All the flexibility happens in this middle stretch, the ax plus b. That's the only thing we can control. And if you think about what we're looking for, we're looking for a line, because ax plus b is a line. So we have to think about, well, what line would work? There's lots of lines, right? I mean, you can draw all sorts of things. That's a terrible choice. And here's another terrible choice. And here's a slightly less terrible choice. Now, why are these two terrible choices? Well, because they don't line up. There's a jump discontinuity at both ends. This is a slightly less terrible choice because at least it matches at one point, but it doesn't at another point. So what's the best choice? We should say the only choice if we want continuity. Well, we need to make sure that we hit these 2 points. So we need the line that goes between them. And once we know that, then it's pretty easy to figure out what the line should be. All right, we got an intercept here. We have to have a slope of 1. So it's going to have slope is 1. So it's x plus, the intercept is 4, x plus 4. In other words, a equals 1, b equals 4. All right, well, That's the first one, right? Good. Progress. Next problem. So, a picture problem. Suppose that f of x is shown in the figure below. All right, so here we go. There's f of x. So we don't know explicitly what it is, but we're going to be able to read the picture. So here's the question. For which values of a between 0 and 4, so I don't care about what's happening outside of there, when is it that the limit does not exist? Now, if we look at the picture, there are certainly two places which catch our eye. And those two places have to be at 3 and at 1. Now, the reason I say that those two catch our eye is because everywhere else we see there's a nice continuous line, unbroken, if you will. So, really the only candidates are at 1 and 3. So let's think about the question. Does the limit as x go to 1 of f of x, does that exist? Yes or no? And the answer is no. Why? Well, because as I come in from above versus as I come in from below, I'm getting different values. Therefore, they don't match up. And if they don't match up, the limit does not exist. Okay, so certainly 1. That's one of our choices. Now, how about 3? Does the limit exist at 3? Well, something's definitely going weird with 3, but what about the limit? Be careful here. Well, let's do it from both sides. As we come in from above and as we come in from below, we're both approaching 2. In other words, we're getting a consistent answer. And so the limit does exist at 3. There is a different type of problem at 3, but as far as the limit goes, it's fine. The limit exists. So it turns out that the answer for 1 is 1. Okay. So let's go to the second problem. How should the function be modified to delete a removable discontinuity? Well, there is 2 points where we have a discontinuity. This first one is a case where it's a jump discontinuity because the 2 sides don't line up. So you're like jumping your pen to keep going. The second point, where it's just at 3, that's removable because both sides come together. It's just that happens to be that the function is not defined in the consistent manner with the behavior locally. So we say, okay, well, how do we want to do it? What we want to do is say, look, this is defined incorrectly. What we need to do is redefine it to fill the hole. So that's our goal, is how do you fill the hole? Well, the coordinate that fills the hole, the input is at 3, the output is at 2, so we should change our function f of 3 to equal 2. And that's how we can modify it to delete the removable discontinuity, because that would fill the hole in. Okay, so that's what we're doing, is we're moving that from there to there. Good, good. Third part. Is the function x minus 1 times f of x continuous at x equals 1? And we should justify our answer. Well, let's think about it. First off, if it's going to be continuous, we need to have 3 things be true. So we need to look at the limit. So let's look at the limit as x approaches 1 of x minus 1 times f of x. Now, the thing is, it's a little bit hard to figure out. So let's actually do this by breaking it up into 2 smaller limits. So the limit as x approaches 1 of x minus 1 times f of x as we approach from below, and we're going to look at the limit as x approaches 1 from above of x minus 1 times f of x. So in other words, if we're trying to understand what's happening, we say, well, let's look from both sides and see what happens. Now, the nice thing is, as we look from both sides, it's a little bit easier to see what's going to go on. So from below, we see that the function is going to approach negative 2. On the other hand, x minus 1, well, that's going to do something as well. that's going to approach 1 minus 1, which is 0. So the net result will be, we multiply them together, we get 0. When we come in from above, what do we see? We're approaching 1. So the function is going to 1. X minus 1 still goes to 0, and that is 0. So, okay, good. So at least the limit does exist. The limit is 0. On the other hand, if we plug in 1 minus 1 times f of 1, well, that's 0 times 2, which is 0. So we see that the limit exists and it equals 0, and the function exists and it equals 0, and of course 0 equals 0. So we've now checked the definition of continuity, and we can say that yes, this function is continuous. Essentially what we are doing here, it's kind of a very simple idea when you think about it. What's happening is x minus 1 is making everything around 1 smaller and smaller, and it's squishing it all down. And so if everything was somewhat well behaved, in other words, it didn't go arbitrarily large, once you multiply by something that's making it very small, the result is it's small, and therefore it is going to be continuous. It fixes the problem. 0 is very persuasive in that way. It does something. All right. Well, let's look at another problem. And this one, just a simple limit, and oh my gosh, we might be here a while. Or maybe not. Okay, let's think about this. This is a crazy looking function. And truly it is. I mean, it's just such an unpleasant function. It's a kind of function that you wouldn't want to take home to meet your parents, because they wouldn't be willing to accept them right away. You got to warm them up a little bit. So what do we do here? Well, what you want to do is you want to say, is this a function which, even if it doesn't look nice, actually is nice? What do we mean by that? So what we mean is it continuous? So what we can do is we can stare at it, and we really are going to think about our building blocks and putting things together. And so let us walk through verbally and decide if it's continuous. So for example, let's start here. Sine is a continuous function. So is the inside continuous? Well, x squared is continuous. E to the x squared, that's a composition. So that's a composition of continuous functions is continuous. 23 is a continuous function. So if I add two continuous functions, yes. So this first part is continuous. X to the fifth is continuous, as is arctangent. Therefore, the product of x to the fifth and arctangent is continuous. 17 is perfectly fine. Sine is a continuous function. Cosine is continuous, so if I plug sine into cosine, it's still continuous. And continuous everywhere. So I have all these pieces on the top are continuous, add and subtract, still continuous. Downstairs, x to the fourth, that's fantastic, 5, loving it. Sine squared of e to the x plus e to the negative x. Well, e to the x plus e to the negative x, both of these are continuous functions. Add them together, yep. Plug it into sine squared, good to go. Log of x squared plus 1. Now, this one is a little bit dicey. Natural log does have problems, but where does natural log have problems? It has problems whenever what you plug in is less than or equal to 0. Aha, but look what we're plugging in. We're plugging in x squared plus 1. Is that ever less than or equal to 0? And the answer is no, because it's the smallest it can ever be is 1. So this is also a composition of a continuous function and a continuous function, and we stay away from the problem areas for log. So everything downstairs is continuous, and when you add a bunch of continuous pieces together, you're still great. It's wonderful. So the moral is this big expression is a continuous function. Now, how does that help us? Well, it helps us because once we understand that something is continuous, the next thing is, let's plug in 2 and see if we get a number. And if we do, that's the answer. So actually, limits of continuous functions are really nice, unless, of course, you happen to stroll across the 0 over 0, which means more work, which I guess is incredibly nice. Because, boy, isn't it fun to do some work? All right, so what we're going to do is say, well, let's see what happens when we plug in 2. Sine 2 squared is 4. So e to the 4th plus 23. 2 to the 5th, well, you can leave it as 2 to the 5th. It turns out to be 32. Arctangent of 2, which is arctangent of 2. Not much you can do with that. 17 cosine sine of 2. Divide that by 2 to the 4th, which is 16, plus 5 more makes 21, plus sine squared of e to the 2 plus e to the minus 2, plus log of 2 squared is 4, plus 1 makes 5. And now we're saying, all right, this will be our answer as long as the denominator is not 0, but we're good to go. 21 is definitely far away from 0. Sine squared is greater than or equal to 0, and log of 5, it's at least 1, and it's not negative. And therefore, there's no division by 0, and we're done. So this is our, hey, isn't it nice to know things are continuous? Because once you know that, you have power. It saves a lot of work. There's no heartache, no crazy algebra manipulation. It's just plug it in. And there you go. Okay. So, the next problem. P of x is a polynomial. It's the polynomial 18x cubed minus 63x squared plus 67x minus 20. That's kind of an interesting looking polynomial. And there's a question. Does this polynomial have a root in the interval between 0 and 1? Okay, so we mentioned root a little while ago when we talked about the basic ideas for continuity. We talked about the intermediate value theorem. So one of the things that could happen is, in the intermediate value theorem, is it's useful if the value that you're looking for is somewhere in between. Now, when we're talking about a root, what does that mean? A root, is it root or root? Well, yes, depending upon who you ask. That means we're looking for a place where a value for x, when we plug it in, and we get 0. So one of the things we can do is we can say, well, let's plug in just 0. Maybe that works. Well, probably not, because you're going to get 0, 0, 0, negative 20. What if you plug in 1? Will that work? Well, let's see. Well, let's add the 18 and the 67 together. That seems pretty reasonable. That would be 85. And then here, subtract 63 and subtract 20, that would be 83. So if I take 85, subtract 83, that gives 2. It's closer, it's not 0, but here's the nice observation. So at 0, we're, say, down here at negative 20. At 1, we're up here at 2. And we have a polynomial. Polynomials are continuous, which means that as I move from this point here to that point there, I have to cross. So that means that there's some place where I'm going to hit an output value of 0. So does this have a root in the interval from 0 to 1? And the answer is yes. It does have a root between 0 and 1. Okay. Well, there's a second part to this problem. Does this have a root between 1 and 2? Let's think about that one. So we already know what happens when we plug in 1. So let's plug in 2. So P of 2. Well, that would be 18 times 2 cubed, which is 2 times 2 times 2, which is 8, minus 63 times 2 squared, that's 63 times 4, 67 times 2, and minus 20. Now, this is probably a point where you're like, it would be nice to have a calculator. For example, these numbers, this first number, it's kind of gross. Okay, that's a little math humor. Well, what is 18 times 8? It's 144. So what's the joke? Well, it turns out that 144 is 12 squared, a dozen dozen. And 1 gross is equal to a dozen dozen. It means 144. Ah, good times. Okay, 63 times 4. that would be 252. 67 times 2 would be 134. And 20, okay, I got that one. That's 20. All right, so let's see. 144 plus 134, that would be 278. 252 and 20, that would be 272, which tells us that we get 6. Ah, nice. So if I update my picture here, here is the next point. So previously we went from down below and we were above, so we had to hit. Now, what do you see? Well, we start here, we have to end up here. So we're now ready to answer our question. Does p of x have a root in the interval from 1 to 2? And the answer is maybe. Now, you probably were expecting me to write down the word no, but that would be wrong because you have to be careful with the intermediate value theorem. You want to say, oh, I'm going to go from here to there, but I don't necessarily have to go directly. It might be the case that we dip down and then we come back up, and so it could be the case that there might be roots. We don't know. That's why you have to be careful when you apply the intermediate value theorem. It can say if I'm below something and end up above something, I had to hit the something. But if I end up start and end below, it doesn't mean I missed it. Or if I start and end up above, it doesn't mean I missed it. It just says I don't have enough information. Now you might be wondering, okay, it could do that, but really, does it do that? And the answer is yes. This function is actually set up so that between 1 and 2, it does cross and have a root. In fact, it has 2 roots. So that's why you always want to be careful. You want to know what something says, but you also want to know what something doesn't say. All right, cool. Fun problem. Good. Okay, well, let's do another one. Okay. Show that there is some value x where x goes between 0 and 1, where cosine of x equals x. Interesting. Now your first response should be, what does this have to do with anything? It seems like a different type of situation here. So let's think back to what we were just doing on the previous problem. If you saw the previous problem, it was the intermediate value theorem. So the intermediate value theorem is really good at saying, when do we have a root? Or at least when are we guaranteed to have a root? So when we're talking about the intermediate value theorem, we can say, okay, well, let's see if I can find some function where I want to get something equals 0. Now you might say, but that's not what we have here. We have a function on the left and a function on the right. That's when we want two functions to be equal to each other, not necessarily one function equal to 0. So this is our great, what we can do is we can say, saying that cosine of x equals x is the same as saying cosine of x minus x equals 0. So in other words, we're going to just move the x across. And now we're saying, really we're looking for a root of this function, cosine of x minus x. So now we do what we always do. We plug things in. F of 0, that's cosine of 0 minus 0, which is 1 minus 0, which is 1. F of 1 is cosine of 1 minus 1. Now, cosine of 1 is not a nice number, but the important thing for us is it's below 1. So, since it's below 1, if I subtract 1, I'll end up with something negative, which means that whatever the function is, it's 1 here, and when we plug in a value at 1, it's negative somewhere. And therefore, there has to be a root. And so that's the argument. So it's sort of nice. The intermediate value theorem is nice because it says, hey, I can show you something exists without actually telling you what it is. And so it's kind of interesting that we have that ability to say that something exists without actually finding it. Now, if you have a calculator, and, I actually don't have a calculator with me, but But if you do have a calculator, some calculators allow you to do this, where if you push a button, you're able to repeat the computation using the current number. So when I was a student a long time ago, and a very long time ago, as you might be able to tell, one of the things I would do is I would sit down and start pushing the cosine button. And it would first pop into a number, and if I kept pushing it, then the numbers would not behave very nicely for a while, but after a while I could see that the numbers were starting to get more and more sort of equal to each other. In other words, it was converging to something. And lo and behold, if you just sit there and keep pushing that, and you do it for a couple minutes, then you're going to end up with this nice number, which once you plug it in, it doesn't change, at least as far as the calculator readout goes. That number is an example where when you plug it into cosine, the output is what you plugged in. So that would be the number you were looking for. This isn't a side note. It doesn't have anything to do with what we've learned, but it's kind of a cute, fun little thing. And I want to just show you the picture about what's happening. So here you go. So we have our function cosine of x, and so cosine of x comes down, and it does something like that. And then we have our function x. It does something like that. What are we after? Well, we're after visually this point right here where they intersect. So here's what would happen if you were to plug something. Let's say we start at 0, plug it into our calculator, and then whatever comes out, we repeat. So when I plug 0 in, so I'm starting at 0, I plug it in and I get 1. So that's the output. Now where does it show up? Well, if I want to repeat it, I'd say, well, come across to this line y equals x, and now here is where 1 is at. But really what's happening is when I plug it back in, I'm going to go back to here. So I started here, moved up, moved across, moved down. Now I got to figure, well, what does that do? Well, it's going to shoot over here. So in other words, the value, the output, is now at this coordinate. Well, okay, now I plug that in. And lo and behold, what's going to happen here is you're going to form this little sort of web. And every time you plugged in, you were going to get a little bit closer. And it slowly but surely zeroes in. And so that's what happens when you plug, repeatedly push that cosine button on your calculator. Now, in a couple of sessions, well, maybe more than a couple, but later on in this class, we're going to actually come back and look at a problem like this and say, pushing that button takes a very long time. We're going to repeat that same process and show that in just a couple of steps, we can get there very quickly. In other words, with high accuracy, get to what that value would be. Okay, anyways, all right, enough foreshadowing of things to come. Back to our problems at hand, right? We still have problems to consider. So, here we go. Determine the value, or possibly values, of a so that the following piecewise function will be continuous. Now, you notice, if we look at our functions, we have e to the 2x plus 10 sine squared of x, and 7e to the x minus 10 cosine squared of x. Now, where does a show up? It doesn't show up in these pieces. So the pieces don't depend on a. Well, where is a? Well, a is where we glue things together. So, okay, that's a little bit different. So let's think about what the intuition should tell us. So what we have is we'll draw a little grid here. So if we're looking for a, well, let's suppose that this first function, I don't know exactly what it looks like, but it does something like that. I don't know, maybe. And right now I'm just working on intuition. Intuition is pretty good to have. So what about the second function? Well, okay, let's say this is our second function. And it's doing something, who knows, maybe something like that. Now, we have to think, where do we spot the a? Well, let's look at some potential places. Could a be over here? The answer is no. Because look, if I'm going to switch, because what happens is at A, we switch from one curve to the other curve. So if I were to do a switch here, that wouldn't be continuous. It would be discontinuous. Okay, well, what about something over here? Same thing. It's a discontinuity because there's a jump involved. Well, what about here? That's fine. You see where they cross, that's a good place to pick A because they're not going to have to be a jump involved. Now, we should be a little bit careful and ask the question, are there any other problems we should be worried about? And there's not. These functions, e to the 2x and 10 sine squared of x, all these individual pieces are continuous, so when you put them together, it's continuous. Same process here, 7 e to the x minus 10 cosine squared of x. So what we're really looking for in order to make this continuous is we have to figure out where to glue them at a crossing point. So our choice for A is going to correspond to any place where I cross. Okay, that's not so bad. We've reduced the problem to saying what we need to do is figure out when does e to the 2x plus 10 sine squared of x, which is our first function, match 7 e to the x minus 10 cosine squared of x. And at first glance, this looks like it's going to be an unpleasant experience because we have e to the x and some trig involved. And they're kind of different functions. We really wouldn't want to have both mixed together. But let's see what we can do. Maybe if we're really nice, it's going to be nice back to us. So one of the oftentimes things you do is you say, let's move everything to one side, because setting stuff equal to 0 is a really nice tool to have. So if we do that, I'll have e to the 2x. I'll bring that e to the x across, put it right next to it, minus 7 e to the x. Now, the trig, they both have 10, so I'll factor the 10 out. So then I have sine squared of x. Then this is a minus cosine squared of x on the right, so on the left, it's going to become a plus cosine squared of x, and equals 0. Now, you see it, right? Sine squared plus cosine squared equals 1. Oh, good stuff, good stuff. So, now we're like, okay, all right, we're making it. E to the 2x minus 7 e to the x plus 10 equals 0. Now, we're closer, but we're still not quite there yet. We have to start thinking, how do we solve this? Now, depending upon your algebra acumen, you might be thinking, well, maybe there's some logs, right? No, logs are a poor choice to make here. At least right now they are. The reason why you're tempted to do logs, other than the fact I just said the word log, is you're like, well, I'd really like to bring this x down. And logs are a great way to bring things out of exponents, especially if I have e to something, the log brings it down. The problem is, the issue is, logs do not get along well with subtraction and addition. So if you have subtraction and addition involved, forget logs. They're not going to help you. Okay, so we don't have that as an option yet. We'll come back. There will be a log involved. Spoiler alert, there's a log coming. So what do we have? Here is a little interesting tidbit. Sometimes we like to hide a square. What do I mean? Look at e to the 2x. There's a lot of ways to write e to the 2x. One of the ways you can write e to the 2x is as e to the x quantity squared. Now you might say, well, yeah, by that logic, it's also e to the 2 to the power x. No, come on. Why do we like e to the x quantity squared? Well, notice this is e to the x. So now we're making things look more compatible with each other. So, okay, it almost looks like a quadratic because it's a quadratic. Now, if you're not comfortable with this, let's just introduce a temporary name. I'll put, say, a capital Y. Y squared minus 7 capital Y plus 10 equals 0, where capital Y, is e to the x. I'm allowed to do this. It's just a temporary place name. It's just holding something for me. Now, if you saw this problem, don't worry about where it came from, but if you just saw this problem, y squared minus 7y plus 10 equals 0, what would you do? Well, probably you would try to factor. And so, we should try to factor. And it does factor. So this factors as y minus 2 and y minus 5. Because what do we need? We need two things that multiply together to 10. There's not many things that multiply together to 10. 1 and 10, 2 and 5. But add to give 7, specifically negative 7. And so that would be the 2 and the 5, make them both negative. So we're almost there. So now we need that y is either 2 or y is 5. This is the advantage of setting something equal to 0. Because if something equals 0, it has to be the case that one of these two things has to be 0. So either the first part equals 0, which is the y equals 2, or the second part equals 0, which is the y equals 5. Now we're not done yet. Let's step back. Y is e to the x. So we're going to come back over here. That says we need e to the x equals 2 or e to the x equals 5. Now log is a good choice. We can take the log of both sides. There's no addition and subtraction happening on the two sides, so log works miracles. Log of e to the x would be x, so x equals log 2, or x equals log 5. And that is the answer. Log 2 or log 5. So it turns out there's two times we could have chosen it. And it's good that we did the work, because I don't think we could have found these just by random guessing. Of course, why would we ever do random guessing? We like to do the work. Okay, good. So let's, one more. This one, it's a good problem. Find the values of a, b, c, which are positive, so a, b, and c are all positive values, and so that the following function is continuous. All right, so, well, we're going to have to dig a little bit here. So we have some pieces. Now, the middle piece is really nice. It's just a flat value. It's always 8. So the middle piece is perfectly continuous. The other piece is 1 minus cosine of ax over x squared. Well, that's continuous, except possibly at 0. So we have to fix that. And then the other piece, well, it's a rational function, so that can be continuous as long as the denominator is not 0, and we'll do some investigation into that. Okay, so let's start at 0. So what do we need? Well, we need that the limit as x approaches 0 from below of f of x has to be the limit as x approaches 0 from above of f of x. Well, but if I'm just above 0, I'm 8. So this means that we need this to be the limit as x approaches 0 from above of 8, which is 8. Okay. So we know what we need to have that be equal to. So what is this? Well, that's the limit as x approaches 0 from below of 1 minus cosine of ax over x squared. So we're going to dig into this a little bit and try to figure out what this limit is. Now, if you remember when we talked about the problem where we did one-sided limits, and in particular sine x over x, we said, hey, we can make this, our goal is to put a sign in the upstairs, and the way we do it is to multiply 1 plus cosine of ax over 1 plus cosine of ax. Because recall, and it's good to recall these things, that there's this sort of fundamental philosophy, and namely, limit as something goes to 0. Well, let's not call it x, let's call it blah. Blah goes to 0, sine of blah over blah is equal to 1. So, oftentimes when I see both trig and a polynomial involved, I'm going to pull this fact out. So that's my goal, is to get a sign. So that's where I'm going when we multiply by 1 plus cosine of ax. So this is our limit as x approaches 0 from below of 1 minus cosine squared of ax over x squared 1 plus cosine ax. Well, that's the limit as x approaches 0 from below. Upstairs, that's now sine squared of ax, and downstairs, that's x squared and 1 plus cosine of ax. Okay, so we're almost there. Now we say, okay, that's the limit as x goes to 0 from below of sine of ax over x, sine of ax over x, and then there's a 1 over 1 plus cosine ax. So in other words, I'm really trying to get the sine of blah over blah. I didn't quite succeed though. Can you see where my slight failure is? And then how to fix it? My slight failure is the inside is ax, the inside of sine. The denominator is just x. I need to get an a down there. Can I do it, and how do I do it? Well, the answer is I put an a down there. All right, well, that's kind of the answer, but that changes the problem. So I just have to find a way to compensate for this new a, and the way I'll do it is I'll put an a up here. Then I'll do the same thing here. Put an a there, and put an a there. Now we have what? This first piece goes to 1. It's the sine of something over something. The something is matched. The inside goes to 0. The second piece goes to 1. This last piece goes to upstairs. A times a is a squared. Downstairs, 1 plus cosine 0. Well, 1 plus 1, which is 2. So we get 1 times a squared over 2, which means we get a squared over 2. Now, run it back. A squared over 2 equals, boom, 8. All right, so we have, updating here, a squared over 2 equals 8, or a squared equals 16. So we need something when we square it to get 16. There's two candidates, 4 and negative 4. But remember, the problem said they need to be positive values. So that tells us a has to be 4. It's the only choice which will make it continuous. Nothing else would work. Well, that was a good problem. Oh, wait a second, we're not done yet. We still have to do B and C. How could I have forgotten? Okay, now the weird thing is we've got to make it continuous at the point 1. That's only like one thing, but somehow we need to get both B and C. How are we going to do that? Well, let's try to figure out what our current problem is. So let's look at what's happening here. So we look at 8, that's the limit as x approaches 1 from below of f of x, because here, as I approach 1 from below, I'm always 8. That needs to match the limit as x approaches 1 from above of f of x, which is the limit as x approaches 1 from above of x minus b times x plus c over x squared plus 3x minus 4. Now, one of our overriding philosophies whenever we're working with limits is plug in 1 or 0 or whatever you're taking the limit to and ask the question, what's the number? And if it's a nice number, we're done. So is it a nice number? Well, what do we have? Well, downstairs, we end up with 1 plus 3 minus 4, which is 0. Upstairs, we end up with 1 minus b and 1 plus c. Now, what's our conclusion? Well, our conclusion is we have something downstairs which is 0. Now, what does that tell us about the numerator? Well, we know we want it to be continuous, so we need to get an answer. If the numerator was not 0, in other words, it was something that didn't produce a value for 0, it would be over. The limit couldn't exist. Because essentially what's happening is when you have a non-zero number divided by 0, it's saying you're blowing up. We can't blow up. So that's telling us we need 1 minus b times 1 plus c has to be 0. Okay. Well, so can 1 plus c be 0? Well, no, c is positive. So that tells us the 1 minus b has to be positive, so b has to equal 1. In other words, if b is not 1, we don't get 0 over 0, can't have a possible limit. Now, so let's update. So we now know this is the limit as x approaches 1 from above of x minus 1, x plus c. And downstairs, we'll see that this factors in that one of the terms is x minus 1, because 1 is a root, and the other term is x plus 4. Now, the x minus 1's cancel, okay? So what do we get? Well, we get 1 plus c over 1 plus 4, which is 5. Now that's perfectly fine, except what do we need? We need that to equal 8. Okay, so 1 plus c, but multiply the 5 across, has to equal 40, or c has to equal 39. Huh, well, that's a kind of a big number. Wouldn't have guessed that. At least it's not obvious that that's the right guess. But that's okay. That's why we do the work. Ah, some good fun problems. Good fun problems. And I guess we're going to keep them going. All right, keep working.